I've been talking about the existential threat of AI. This is a longer-term threat. There's many, many short-term threats which are urgent, like cyber attacks and loss of jobs and pandemics, and they go on, fake videos. But there's this longer-term existential threat that we will create things more intelligent than ourselves, and they will take over. Many people don't take that seriously, and one of the reasons they don't take that seriously is because they don't think that the current AI systems we have really understand. So there's a group of people, many of them linguists influenced by Chomsky, who call these things stochastic parrots. And they think these things are just a statistical trick that takes a big body of text and just pastiches things together and looks like it understands, but doesn't really understand the way we do. Now, to have that theory that they don't understand the way we do, you have to have a theory of how we understand. I'm going to argue they understand just like we do. So the people who talk about stochastic parrots, they have a theory of understanding that comes from classical symbolic AI, that in your head you have symbolic expressions in some cleaned up language and you use symbolic rules to manipulate them. That theory never really worked, but they still stick to it because somehow they think the only way you could have intelligence is by having something like logic to do reasoning with. And they think the essence of intelligence is reasoning. There's a completely different paradigm, which is the essence of intelligence is learning, and it's learning in a neural net. And things like vision and motor control are primary, and language and reasoning comes later. But I want to address this issue of, do they really understand? And there's one particular piece of history that most people don't know, which is these large language models, which certainly appear to understand and can answer any question you ask them at the level of a not very good expert, they came a long time ago. I like to think like this. They came from a model I did in 1985, which was the first neural net language model. It had 104 training examples instead of a trillion, or many billions. It had about 1,000 weights in the network instead of a trillion. But it was a language model that was trained to predict the next word and to backpropagate errors from the prediction in order to convert input symbols into vectors of neural activity and then learn how those vectors should interact to predict the vector for the symbol it was trying to predict.
Imagine you happen across a short movie script that describes a scene between a person and their AI assistant. The script has what the person asks the AI, but the AI's response has been torn off. Suppose you also have this powerful magical machine that can take any text and provide a sensible prediction of what word comes next. You could then finish the script by feeding in what you have to the machine, seeing what it would predict to start the AI's answer, and then repeating this over and over with a growing script completing the dialogue. When you interact with a chatbot, this is exactly what's happening. A large language model is a sophisticated mathematical function that predicts what word comes next for any piece of text. Instead of predicting one word with certainty, though, what it does is assign a probability to all possible next words. To build a chatbot, what you do is lay out some text that describes an interaction between a user and a hypothetical AI assistant. You add on whatever the user types in as the first part of that interaction, and then you have the model repeatedly predict the next word that such a hypothetical AI assistant would say in response, and that's what's presented to the user. In doing this, the output tends to look a lot more natural if you allow it to select less likely words along the way at random. So what this means is, even though the model itself is deterministic, a given prompt typically gives a different answer each time it's run. Models learn how to make these predictions by processing an enormous amount of text, typically pulled from the internet. For a standard human to read the amount of text that was used to train GPT-3, for example, if they read nonstop 24/7, it would take over 2,600 years. Larger models since then train on much, much more. You can think of training a little bit like tuning the dials on a big machine. The way that a language model behaves is entirely determined by these many different continuous values, usually called parameters or weights. Changing those parameters will change the probabilities that the model gives for the next word on a given input. What puts the large in large language model is how they can have hundreds of billions of these parameters. No human ever deliberately sets those parameters. Instead, they begin at random, meaning the model just outputs gibberish, but they're repeatedly refined based on many example pieces of text. One of these training examples could be just a handful of words, or it could be thousands, but in either case, the way this works is to pass in all but the last word from that example into the model and compare the prediction that it makes with the true last word from the example. An algorithm called backpropagation is used to tweak all of the parameters in such a way that it makes the model a little more likely to choose the true last word and a little less likely to choose all the others. When you do this for many, many trillions of examples, not only does the model start to give more accurate predictions on the training data, but it also starts to make more reasonable predictions on text that it's never seen before. Given the huge number of parameters and the enormous amount of training data, the scale of computation involved in training a large language model is mind-boggling. To illustrate, imagine that you could perform 1 billion additions and multiplications every single second. How long do you think that it would take for you to do all of the operations involved in training the largest language models? Do you think it would take a year? Maybe something like 10,000 years? The answer is actually much more than that. It's well over 100 million years. This is only part of the story, though. This whole process is called pre-training. The goal of auto-completing a random passage of text from the internet is very different from the goal of being a good AI assistant. To address this, chatbots undergo another type of training, just as important, called reinforcement learning with human feedback. Workers flag unhelpful or problematic predictions, and their corrections further change the model's parameters, making them more likely to give predictions that users prefer. Looking back at the pre-training though, this staggering amount of computation is only made possible by using special computer chips that are optimized for running many, many operations in parallel, known as GPUs. However, not all language models can be easily parallelized. Prior to 2017, most language models would process text one word at a time. But then, a team of researchers at Google introduced a new model known as the transformer. Transformers don't read text from the start to the finish. They soak it all in at once, in parallel. The very first step inside a transformer, and most other language models for that matter, is to associate each word with a long list of numbers. The reason for this is that the training process only works with continuous values, so you have to somehow encode language using numbers, and each of these list of numbers may somehow encode the meaning of the corresponding word. What makes transformers unique is their reliance on a special operation known as attention. This operation gives all of these lists of numbers a chance to talk to one another and refine the meanings that they encode based on the context around, all done in parallel. For example, the numbers encoding the word bank might be changed based on the context surrounding it to somehow encode the more specific notion of a riverbank. Transformers typically also include a second type of operation known as a feed-forward neural network, and this gives the model extra capacity to store more patterns about language learned during training. All of this data repeatedly flows through many different iterations of these two fundamental operations, and as it does so, the hope is that each list of numbers...
I'll stop the video here just to highlight what Geoff Hinton was talking about, the pictorial representation of the vectors in three-dimensional space, which is shown here clearly.
Numbers is enriched to encode whatever information might be needed to make an accurate prediction of what word follows in the passage. At the end, one final function is performed on the last vector in this sequence, which now has had a chance to be influenced by all the other context from the input text, as well as everything the model learned during training, to produce a prediction of the next word. Again, the model's prediction looks like a probability for every possible next word. Although researchers design the framework for how each of these steps work, it's important to understand that the specific behavior is an emergent phenomenon based on how those hundreds of billions of parameters are tuned during training.
Just another pause to highlight the term used, emerging phenomenon. Basically, we don't know how it works. Fascinating, isn't it?
This makes it incredibly challenging to determine why the model makes the exact predictions that it does. What you can see is that when you use large language model predictions to autocomplete a prompt, the words that it generates are uncannily fluent, fascinating, and even useful.
A big shout out to a YouTube channel called 3 Blue, 1 Brown. This guy makes fantastic animated explanations about deep learning. I highly recommend that you visit his site and have a look at these wonderful videos.
Now the point of that was not, it didn't have an engineering point. The point of it was a theory of how people could understand the meanings of words. So the best model we have of how people understand sentences is these language models. That's the only model we have of how people do it that actually works. We have all these symbolic models. They don't really work very well. They're influenced strongly by Chomsky, who managed to convince many generations of linguists that language is not learned. On the face of it, it's just obviously absurd to say language isn't learned. And if you can get people to believe something obviously absurd, then you've got a cult. And Chomsky's had a cult. Language is learned, and we now can see things that learn language. The structure doesn't have to be innate, it comes from data. There has to be innate structure in the neural network and in the learning algorithm, but all the structure of language you can just get from data. Chomsky couldn't see how to do that, so he said it must be innate. Actually, saying it must be innate and it's not learned is really stupid, because that's saying evolution learned it rather than learning, and evolution is a much slower process than learning. The reason evolution produced brains is so you could learn stuff faster than evolution can make it innate. So the point of this ramble was to convince you that they understand the same way we do. And I'll give you one more piece of evidence for that. So many people who talk about stochastic parrots say, look, I can show you they don't really understand because they just hallucinate stuff, they just make stuff up. Those people are not psychologists. They don't understand that they shouldn't use the word hallucinate, they should use the word confabulate. And psychologists since the 1930s have been studying human confabulation. A psychologist called Bartlett. And people confabulate all the time. If you take any event that happened a long time ago and that you haven't rehearsed in the meantime, and you try and remember it, you will confidently remember all sorts of things that are wrong. Because memory doesn't consist of getting a file out of somewhere. Memory consists of constructing something that seems plausible.
Here's a fascinating insight from Geoffrey Hinton about what's commonly known in large language models, the fact that they hallucinate. Well, his analogy is brilliant, and it also brings closer the theories that neural nets hallucinate. Humans do the same thing, and these models, which adopt the same structure in the neural net, also hallucinate. Just brings it closer together that we are sort of on the right track in trying to mimic the human brain. Fascinating.
Now, if you've just seen something, and now you try and construct something that seems plausible, you'll have fairly accurate details. But if you saw it many years ago, and you now try and construct something that seems plausible, first of all, it'll be influenced by all the stuff you learned in the meantime. And you'll construct something that sounds good to you, but actually many of the details that you're very confident about will be just wrong. It's hard to show that, but there's one case studied by a psychologist called Ulrich Neisser, which is beautiful. John Dean testified at Watergate under oath about the cover-up going on in the Oval Room, the Oval Office, and he didn't know there were tapes. So you've got someone trying to tell the truth about things that happened a few years ago, and much of what he said was not true, but he was clearly trying to tell the truth. He'd say, there was this meeting between these people. No, those people never had a meeting. And this person said this. No, that person didn't say that. Somebody else said that in a different meeting. But the point is, he was conveying the truth about the cover-up, and he was confident that what he was saying was true, and he was just wrong. And that's just the way human memory works. And so when these things confabulate, they're just like people. People confabulate. At least I think they do. I just made that up. Okay, I'm done. For a long time, in the 90s in particular, within computer science, not within psychology, but within computer science, almost everybody said this stuff's rubbish. They said that in the 70s too. So in the 70s and the 90s, they said this stuff is just nonsense. It's never going to work. The whole idea that you could take a network of simulated neurons, which aren't that like real neurons anyway, and you could make random connections, and then you could get it to do intelligent things just by looking at data. That's ridiculous. You have to build in lots of innate structure for it to do anything at all. And that wasn't such an unreasonable position. They said things like, if you start trying to train it by gradient descent, it's going to get stuck in local optima. They never actually checked whether that's what happened, but they were confident that would happen. And so the question is, how do you keep going when everybody around you says what you're doing is rubbish? And for me, it was quite simple because my parents were both atheists. And when I was 7, they sent me to a private school that was Christian. And so there were all these other kids who believed in God and all the teachers who believed in God. And it was obvious rubbish. I mean, it just was ridiculous what they said. And it changed with time, of course. When we were little, it was an old white man behind the clouds, of the kind painted by Michelangelo. When we were bigger, it was sort of more obscure. But it just seemed to me always, this stuff is just nonsense. And so I had this experience from a very young age of seeing stuff that seemed to me to be nonsense and turned out to be nonsense. And that was really useful for doing neural nets. So what worried me at the beginning of 2023 was something that was obvious for a long time, but I hadn't felt the full emotional impact of it, which is that digital intelligence might just be a better form of intelligence than what we've got. We're basically analog. It's sort of 1-bit digital for neurons, but basically analog. And you can do things with very low power if you're analog, if you learn to make use of the peculiar properties of the analog hardware. So you can't get 2 analog computers to do exactly the same thing as each other, but if each one learns, it can still do things very well, and that's what brains are like. I can't share weights with you because there's no one-to-one correspondence between my neurons and your neurons. So you can be very low power, but you can't share. So we can't have 1,000 different people go and take 1,000 different courses, and as they're doing the courses, they average their weight changes together, and by the time they've all finished doing their courses, they only do 1 course each, but in the background they're averaging weights. And at the end, they all know what's in all 1,000 courses. But that's what these digital intelligences can do. So they have a bandwidth of sharing of the order of the number of weights, so trillions of bits they can share. You and I, the way we share is, I produce a sentence, and you try and change your synapse strengths, your brain does, so that you would tend to say the same thing, if you trust me. And that's sharing with a bandwidth of a few bits per second, not trillions of bits per fraction of a second. And in that sense, they're just much, much better at acquiring lots of knowledge and seeing the relationships between all these bits of knowledge. So to store all the knowledge in only 1 trillion synapses, they have to do lots and lots of compression. And compression means finding what's common to many things and using what's common to them to store them. So you store them by the common bit plus a few differences. And that means they're seeing all sorts of analogies people have never seen between remote fields. And so I think they're going to be much more creative than us.